So I wanted to welcome everyone as people are hopefully coming in to our 2023 edition of our research webinar series. These are a group of webinars that the research committee and ASES has put together to hopefully provide some element of information for our members to be able to help stimulate better research that they're performing, as well as potentially grant submissions. The first topic for our first webinar of the year is on augmented and mixed reality in shoulder surgery, as well as artificial intelligence. We're really lucky to have three wonderful people that I know really well be able to take their time from their lives to be able to help us better understand these. Talking about artificial intelligence in shoulder surgery, Howard Routman from Atlantis Orthopedics is going to be able to give us some information with regards to that. Joaquin Sanchez-Sotelo from Mayo Clinic is going to go over mixed reality in shoulder surgery. And then John Bell from Dartmouth is going to talk about augmented reality. The webinar should last approximately about an hour and 15 minutes. We will do 3 talks, and each one will be followed by about 10 minutes or so of questions and answers. If you have questions, just write them into the chat, and we'll be able to bring these up, and I'll have the team respond to those as those come in. And finally, we've been tremendously lucky to be able to have Exactech sponsor this series for us. It's going to help the team be able to provide a better product in the future. So again, we truly appreciate the sponsorship. And with that, I will hand it over to Howard, and Howard's going to again kick us into learning about artificial intelligence.
All right. Well, can you guys see my screen?
Looks great.
All right, guys. Well, Bob, thanks for inviting me. Bob asked me to come and do a little bit of a recounting of the personal journey that we sort of went on, sort of stepping into the AI and machine learning side of research with the Exactech team. So the goals of this is to talk about the work that we've done with a data and analytics group out of Seattle using AI and supervised machine learning. Talk about some of the work that we've done with it, and also talk about some of the things that we have coming down the pike that are extensions of the existing work that we've done. Really important to disclose that I have a financial relationship with Exactech, and it's very relevant to this presentation. Also, that some of the concepts that I'm going to discuss are not yet incorporated into tools, products, or applications that have been released for patient care. So my personal story is I contributed over 1,200 arthroplasty patients to a registry that has now over 15,000 patients in it with a group of surgeons. And with the appropriate resources, we were able to have a reasonably clean database, and it's the largest of its kind. And we've published over 70 peer-reviewed publications, and these are some of them that you might recognize. It's all these, originally were just regular analytics that we were just presenting our findings, but then we got into a serendipitous situation where in 2018, we were doing a meeting in Seattle, and we already had 10,000 patients in the database, and it was costing like $2 million a year for Exactech to maintain this database and curate it. Over 8 million pieces of individually labeled data. And we set up a meeting with Kensai. So Kensai is a healthcare analytics company. And what's interesting about Kensai is the guy that was running the show was the guy who ran the Netflix prize. So for those who don't know what the Netflix prize was, back in the day when Netflix was a company that delivered DVDs to your house and weren't streaming, they had to buy DVDs and make sure they had them available to send them out. And they were having a hard time guessing which DVDs to buy. So they put out a prize out there saying, if you can improve our existing prediction software by a certain percentage, you'll get $1 million. And the guy that ran Kensai was the guy that ran the Netflix prize. The team that won it was from Bell Labs, no relation to John Eric, but they won and they got $1 million, and they launched what many people think was the field of predictive analytics, which is the use of algorithms, data, machine learning techniques to predict the future based on past past activities, which would be nice in shoulder arthroplasty, because if we look at reverse shoulder arthroplasty in particular, if this is a scatter plot looking at range of motion and outcome scores, you can say that most people do well, but somewhere scattered in between the patients that do well after reverse shoulder replacement, there are some that do worse, and they're sort of hidden within the mix, and they're a little bit hard to pluck out. So using predictive analytics, it might be helpful. So I had to figure out how this works, because I'm certainly not a data scientist. And what I learned was the difference between computer programming and machine learning is rather different. So in computer programming, like what you learned in high school, you have data, you have a human written program or algorithm, you expose the data to the algorithm and it spits out a result, like your mortgage amortization schedule. You know how much you're putting down, you know how much the house is, you know your percentage rate, you know how many years, and it spits out that for you. Machine learning is very different. Machine learning, you have to approach with data and results. And then you ask the computer to create an algorithm or a software program that could effectively predict the results based on data that you're showing it, and then see how good of a job it does with data that it hasn't seen yet. And that's how you evaluate the quality of your algorithm. And this is what Netflix needed, because they had needed to figure out what the next movie I was going to pick. If I've watched Reservoir Dogs 5 times in a row, what's the next movie I'm going to pick? They'll figure something out. And it's very different. Statistical models are designed to look at inference between the relationships between variables, and machine learning models are designed to make predictions and require significant computational power. Supervised machine learning is what we use, and that's when you take labeled observations like our data set, you separate it randomly into a training and testing set. You then expose the training set to the machine learning application, which then creates a prediction model. And the way you test to see if you've done a good job is you then expose this model to data it hasn't seen yet, and you see if it does a good job predicting the results in the test set. And sometimes you can do a really good job on your training set and a crap job on your testing set, and that's called overfitting. And you had to learn all these different things when we're going from standard statistics and analysis to working with machine learning. So it was a fun learning experience for all of us, because none of us were data scientists, and we all had to figure out how to make sense of all of this. So this is our first project, our first paper that was published in 2020 in Core. And what we looked at was, is it even possible to use machine learning to predict outcomes in shoulder arthroplasty? So this was like a feasibility study. And what we found was we used 7,000 patients. We excluded revisions. We just had a number of primary anatomics and reverses. And what we found was that we were able to predict, using pre-op data only, with between 85 and 99% accuracy, that a patient would hit MCID for the thresholds that we measured, which was pretty impressive. But the number of inputs were 291. Totally unfeasible for a research project. You can't track that many people in your office and then use that as a tool. So then we started to identify that the tools that we had feature ranking capacity, where you could rank which inputs had the biggest impact on the result. So we did a second study trying to pare that down as much as we could. And we went down from 291 inputs to 19. So using feature ranking, we reduced the number of inputs to 19. And you can see here that when you compare the full model to the abbreviated model, the precision, recall, and accuracy were actually rather similar. So now we had something that was actually clinically useful. And we created with that this software called Predict Plus, which is a clinical decision support tool approved by the FDA. You enter in the 19 preoperative variables, which are age, weight, height, gender, previous operation on the shoulder, will it be the dominant side, the diagnosis, whether it's osteoarthritis, whether you want a prediction for anatomic or reverse, a couple of comorbidities, a functional score, range of motion, and some pain scores, and it spits out predictions about range of motion and pain and shoulder scoring systems that allow us to be able to have conversations with our patients and say, well, in this situation, if you had an anatomic, the red line is MCID, the green line is SCB, and you can predict improvement of abduction above SCB all the way out to 7 years. Similarly, you can look at range of motion, elevation, external rotation. We even have the ability to predict internal rotation, which is pretty ridiculous for reverse shoulder replacement. And importantly, you can predict complications for anatomics and reverse. And this can be used in many different ways. Some folks use it in the office to talk about patients as part of their consent process. I've used it in the past to try to convince patients they weren't ready for a shoulder replacement. It can be very helpful to show them where they are versus where they'll be. And this is what we did as our second or third project. The third project, we looked at the predictive value and legacy scoring systems using machine learning. And this was an eye opener for me because we were trying to find out if the scoring systems that we've been using for years, actually, if the questions that they ask as a part of their scoring system, if the questions they're even asking are predictive of their ultimate score. And using all 291 inputs, we looked at predictive algorithms for ASES constant UCLA score, and we ranked the variables that had the most predictive influence over each score. And what we found was that most of the ASES constant component questions were of minimal predictive value. And this is almost entertaining that when you look at the 2-year ASES constant UCLA score, and you look at the top 5 most influential questions that impacted that score, only one thing in the top 5 for the ASES score was actually in the ASES score. So the pre-op ASES score was predictive, but it was less so than these other 4 things. Similarly, the only thing that was predictive to the constant score was pre-op abduction, and none of the components of the UCLA were actually predictive of the UCLA score in 2 years. So what we found was that we were asking all these questions and we're tracking all this stuff, but the questions we were asking weren't really that necessarily predictive of our outcome. And the least predictive things were the ones that were task-specific items, like can you put a penny on a shelf or can you do certain things with your arm? And the PROMIS score, which has had a tremendous amount of financial backing with the National Institute of Health, is almost exclusively task-specific items. So what we started to do next was it might be an opportunity to create a shoulder arthroplasty specific score using machine learning techniques. And that's what we did. Papers 4 and 5 were the development and the validation of a machine learning derived clinical metric specific for shoulder arthroplasty that only has 6 inputs. It has active forward elevation, internal rotation, external rotation, pain on a daily basis, pain lying on the side, and your ability to use your arm on a 0 to scale to 10. And we compared this to a bunch of other scores looking at psychometric properties. And what we learned in this process was that a lot of the legacy scores have serious floor and ceiling effects, meaning that patients automatically score the lowest or automatically score the highest, which impacts your ability to discern at the extremes what the differences are. You would like there to be not a lot of patients with 100% scores. And if you look at the floor effect for the constant scores, 72% of the patients in our group had a floor effect because they couldn't do the strength assessment preoperatively. You ask them to do it, and they say, "Oh, it hurts too much. I can't do it." So they're unable to do it. So they get the lowest possible score. Similarly, when you look at the ceiling effects, you had 52% of people with the SST hitting the highest possible score for anatomic shoulder arthroplasty. Now, some might say that means that they do so great, but in reality, you're missing out on an opportunity to discern between the best results. Similarly, the ASES and the 25% ceiling effect. And when you look at the shoulder arthroplasty SMART score, those effects didn't happen. In addition to having significant ceiling and floor effects, there was bias identified where we saw that there was gender and race bias built into these scores that weren't present in the shoulder arthroplasty SMART score. So Bob has pointed out that the data set is imperfect, but there are some benefits to the data set that we have. It's very generalized, 30 different locations, only from patients that have had arthroplasty. So this isn't a great tool for patients who haven't had an operation or are not going to have an operation. It's all with one prosthesis, and maybe we might be asking the wrong questions, but we've had a lot of fun working with predictive analytics and machine learning to evaluate what could be coming down the road. And what's exciting to me is the next step, which is taking our current data set, which does have the Gormley classification in it, but we found that the Walsh classification is actually not predictive of outcomes. But we have this other huge set of data from our preoperative planning software. And originally the FDA had forced us to keep those 2 data sets separate. We were now allowed to then break the glass between those two data sets and the patients that had preoperative CT scans and had outcomes within the data set, we're now merged them together. So now we're able to do a machine learning analysis of the DICOM data on the CT scans, which is crazy because that allows us to do something called computer vision. And this is the final 3 minutes of the talk, but I think this is really exciting. Computer vision is when you teach a computer to see things. Okay, if anyone drives like a Tesla or any of these modern cars, if you've ever been in the car and suddenly it just slams on the brakes for no reason, you're like wondering why the heck did the car just hit the brakes? It's because the camera saw something and the camera analyzed it and thought it was a danger. So computer vision techniques allow you to classify objects. It'll tell you that's a cat, or you can say, well, the cat's in the bottom corner of the screen. It can identify that. You can detect object and other landmarks, and it can also segment your items, which gives you a lot of information about what you're looking at. There's been a bunch of this in medicine already, but it's mostly in cardiology, pathology, dermatology, and ophthalmology. And these computers can look at everything. Whatever we're looking at, they can look at. It can learn how to look at MRIs, ultrasounds, histopath slides. Here's one example that blew my mind when I looked at it. This is the machine learning analysis for using computer vision, looking at chest x-rays. The computer was able to learn how to diagnose pulmonary lesions. And it was able to do it as well as board certified radiologists. It identified where the lesion was and then characterized it as a tumor, pneumonia. What was interesting is that they were, one, able to do it, and two, when the radiologist looked at the 420 chest x-rays, it took 240 minutes for them to do it. And the computer did it in a minute and a half. And so the power of computer vision and using computers to be able to analyze things for us is huge. So how can we incorporate this into shoulder arthroplasty? Well, some folks have already started. Werthel and the group started to look at volumetric assessment of the rotator cuff. People are also looking at bone configurations. What we're doing is we're looking at muscle first. We're looking at rotator cuff muscle, deltoid muscle, and we're making our way into bony analysis. I think that this is going to, unfortunately, usher in the end of the Walsh classification and things like that, because we're going to find things that are actually predictive of outcome. So how could we be using this? Well, the dream sequence is we get a patient with a CAT scan. We plug their stuff into the computer vision, which is a part of the 3D planning tool. You start making decisions with your 3D planning tool, and automatically you start to see predictions come out of what happens to the patient's outcome when you make different changes based on their bony anatomy, their soft tissue integrity, and you can see where you're going by making decisions. So it could be some component of a holy grail for us. When we look back now, our previous state of play was we had the patient outcomes data set that was separated completely from the CT scans that were entered into the preoperative software. By breaking the glass between, we're now able to teach computers to see the CAT scans, have this information entered into our data set, and then give predictions and guidance to surgeons enmeshed in the planning tool. So that's what the next generation we hope will look like. We'll continue to try to layer GPS planning into the computer vision project, then hopefully identify pathoanatomical triggers that would change what we do that's better than our existing prediction. And this can really only be done if you have both outcomes and advanced CT imaging. So in conclusion, that's what we're working on. That's the journey that we've been on, using AI and machine learning to not only look at the prediction of outcomes, but to now analyze CT scan data, both soft tissue and bony, to give us guidance in terms of what we can do down the road when our patients are being evaluated for arthroplasty. And that's it. I'll stop sharing and I'll send this over to Bob. Thank you.
Howard, great work, and taking a really complicated topic and making it relatively straightforward for us to be able to at least get a picture of what's going on. I think your last, for me at least, the last couple of slides answered the question that I was going to ask in the first part of the talk. And my understanding of Predict Plus is that, one of the things that at least my understanding of the 19 different variables that are 19, I think it's 19 different variables, is it's not necessarily about version inclination of implants and glenosphere size and thickness of poly and et cetera, all these variables that we have surgically that could then potentially influence outcomes. They are more patient-based factors as opposed to necessarily implant-based factors. And it seems like with this new iteration, you will be including, because you're including the preoperative plan and the decision-making, that will allow you to change implant variables to then try to optimize that for the specific patient that you're treating. Is that correct?
Right.
In line with
That's
what's
true.
going on?
Yeah, that's in line with what we're doing. There's one other wrinkle is that when you're using navigation at the time of surgery, when you put your implant in and you have your final position, part of the GPS data set is the saved final position of the implants that are being put in there.
Yep.
And the other decisions that, like you're talking about, like polyethylene thickness and where your humeral cut will ultimately be made, those types of things, since they're going to navigate in the humeral side, we'll be able to actually save and store all that into the patient specific side, and then roll that back to the preoperative variables and be able to hopefully give some guidance in terms of where the sweet spot is. And we've been trying to talk about where the biomechanical sweet spot is for the center of rotation for quite some time. But hopefully we can get some guidance from saving all this stuff.
Yeah, the key is understanding the exact position of where the final implants are. And I think that has been a challenge for most companies that are out there that, with beyond doing CT scans on patients post-operatively to identify the exact position, we're just basing a lot of our presumptions that the preoperative plan equates to what the final position of what the implants truly are. And we know that is not necessarily the case. And so, and if you're going to start integrating those variables into a decision-making process of what's the optimal treatment, then you need the exact position of where those implants are to include them accurately. So yeah, it's interesting. Joaquin, do you have any questions, or John?
Yeah, I have so many. Howard, that was an amazing presentation. This is so exciting. So I have a couple of questions. Looking into fat infiltration using computer vision, we've done some work in that field as well with computer vision. And what we have learned is that looks like fat infiltration is not homogeneously distributed in a muscle. What I mean is that if you take a muscle that is fusiform, you may have some spots where there is some fat and some there is more muscle. So if you use only one slice, you will be capturing that slice fat infiltration, but not the whole volumetric fat infiltration. And number two, I've never liked very much the occupation ratio because, again, the supra is fusiform. So if you have a torn tendon and it retracts, then you're getting a cross-section that is smaller as a function of the retraction. Now, in the intact calf, that's different. But my question is, do you plan to use this type of computer vision on every slice of the T2 parasagittal or just one? Because that will change dramatically two things, accuracy and also computer power. We've been doing some plain X-ray computer vision studies at Mayo Clinic, and it's incredible the computer power that you need just to get one X-ray analyzed in 10,000 patients. So if you have to now analyze maybe 50 sections per shoulder for 15,000 patients, you will use Google and Netflix servers and you will still not have enough. So how do you plan to overcome that? So
what we learned when we started to do CT scan computer vision was a couple different things. First was that each CT scan manufacturer has, we think as orthopedic surgeons that DICOM data is raw DICOM data. And it means that is like the source code of the CT scan, when in reality, that's already been modified before it becomes DICOM data through a filter. And that filter is called a kernel of some type, right? So that, and the thing is, each CT scan machine brand applies different kernels to their different slices, to their different studies, which makes it very difficult to back things all the way out to the raw source data. So that was our first challenge, is that understanding that you could have 3 different CT scans on 3 different patients that all qualified based on quality to be used in GPS preoperative planning. But it's like someone's put 3 different Instagram filters on them that you can't get off. And it really changes your ability to really analyze them. So we had to go backwards and figure out how to detach that from the actual images. The second thing was, yes, looking at it in just one slice really does take away from the analytic value. So it's the CT scan that we get for GPS includes the entire scapula. So one of the things that's being measured is the entire vault for the supraspinatus, the fossa and where it's supposed to sit. Separating the infraspinatus and teres minor is not easy. They are just right on top of each other and difficult to sort of separate out. And some of the more exciting stuff has come from the analysis of the deltoid. And looking at the deltoid specifically, we're learning a lot. The bony components of it, I thought it was going to be easy to say, let's just look at Hounsfield units. But the truth is, with all the different filters, they're different. And it's challenging to work that out. So this is going to be a work in progress for a bit, but we've made a lot of progress in a short period of time.
Okay. Great questions and really interesting work, Howard. So we can think a little bit more. If there's other questions, we can circle back to at the end of the talks. I'm going to get to John. John, you can pull up your talk at this point. So John's going to give us a brief talk about augmented reality, how he is currently using this in the operating room for shoulder arthroplasty and what he's learned from this. So John, the floor is yours.
All right. Thanks, Bob. Can everyone hear me? Great. All right. So I do have a, hold on one sec here. All right, so I do have a relevant disclosure as well. I've been working on the development of the Nexstar, which is the augmented reality technology with Medacta, which is what I'm going to talk about tonight. Thanks for the opportunity to join this awesome panel. So just a quick overview of what reality actually is. We all live in reality, but there's a continuum all the way over to virtual reality. And in between is mixed reality, which Joaquin is going to talk about. Virtual reality is something that I've been playing games with my kids using this Oculus Quest. This is our favorite game here called Beat Saber. But it's not just for gaming. It's also entering the arena for orthopedic education, teaching residents and other applications. Augmented virtuality is another type of reality that we, sometimes hear about, but this is not quite as fleshed out. My wife's an interior designer, and you can use sort of apps like this to place real world objects into a virtual environment and see how things might look. And then augmented reality, which is what I'm going to talk about, is when you overlay digital images into real space. And so there's 3 different types: projection-based, video see-through, which is this Pokemon Go you've probably heard about, and then optical see-through, which is the technology we're going to talk about tonight. So the system I've been using has basically 3 hardware components. There's the instruments, the monitors, and the glasses. We affix the tracker, which is a small, it's about an inch square, to the coracoid using small pins. They're about the size of metacarpal X-Fix pins, and they're affixed there. That's pretty good fixation. It has to be very robust and not move at all, or else you kind of lose the ability to use the AR. And this tracker will then communicate with a camera that's swapped out between different instruments. So whether you're using a K-wire driver, or a drill, or a reamer, they're communicating directly using infrared technology. And it's pretty accurate. Studies from the company have shown 1/2 degree and 1/2 millimeter accuracy in ideal situation. So this is how it looks. This is me with my hood, my N95, my headlight, and my AR glasses. So not too overwhelmingly burdensome. One nice little feature about having glasses like this is there's a camera in them, so you can actually record your surgeries from a surgeon point of view without, snapping a GoPro onto the top of your head. And I'll have a video a little bit later that shows some of that. So the surgical workflow, the first step in doing anything that requires navigation is registering the scapula. And so basically that means teaching the computer where the scapula is in real time. And so in this situation, we use this little pointer device, and we touch these predetermined points on the glenoid. So this is what it looks like at the end of the registration. We've touched 30 different points between the coracoid and the glenoid, and that gives the accuracy that's needed for the case. So once we've got the scapula registered, we can start by placing the K-wire, which will give us our inclination, version, and start point for the base plate. And so this is how it looks. So on the left side is what you're seeing through the glasses, and that sort of icon is superimposed onto the surgical field, and you can sort of put that where you want. I found that if you put it right in the center of your central vision, it's actually kind of annoying and gets in the way for the rest of the case. So I have it just a little bit above my central vision, so I don't really have to look away at all from what I'm doing, but I can still see it. And so what I'm trying to do is place the dot in the center of the circle. So the circle represents the start point from the preoperative plan on the computer. Once you get the circle in the dot in the circle, then you can adjust your horizontal hashes, which is going to be your inclination. And then you can adjust your vertical hashes, which is going to be the anteversion, retroversion. And so if you can get that all aligned, you'll put the guide pin in the same place that you had the preoperative plan. And so in the glasses, you can only see the hash marks. But if you look over at the monitor, you can see these DICOM images if you want that level of detail. But in reality, not having too much information in the glasses is actually nice because it can get distracting. So the next step is reaming. And so in the glasses, you see a little, we call it a gas gauge, which is the little bar. And as you ream more medially, you fill that up. And so the target in this case would be 2 millimeters of reaming. And then you can kind of see where you are as you progress medially to get the full seating of the base plate. The next step is drilling the central hole. And then putting on the base plate actually is helpful to use the AR for this because you can optimize the rotation of the base plate so that the screws will coincide with the best bone. And so when I do my pre-op plans, I'm looking at where the screws are going to wind up. And then I can replicate the rotation of the base plate so that the screws will get into the best bone. And so here you can see if you rotate the base plate, the little dot will go out of the circle. And then if you get it right back in there, then you've got your screws optimized. The next part is placing the screws themselves. And this is done directly on the DICOM images. And so you have biplanar DICOMs, axial and coronal. And you can basically just steer the screws into the best bone in real time. And then lastly, this is a video of that. You can see that as you rotate your hand, the screw changes in its trajectory. And then lastly is putting the glenosphere on. And so again, controlling rotation of the glenosphere, since it's offset, is helpful because you can then maximize the offset at the site of the potential impingement inferiorly. Because sometimes it's not directly inferior, it's a little bit anterior or posterior. So here we are rotating the sphere to get that offset in the perfect spot. So that's basically how the AR system works, the workflow of it. At the end of the case, and this is to the point that Bob and Howard were just talking about, you get a report back, and the report tells you exactly where you place the implant. So you know exact inclination, version, reaming depth, so you have an idea of your medialization. And you can even tell where the rotation of the offset glenosphere was, so you can potentially determine where there may have been points of impingement if you have a complication, you decide to go back. So from a research standpoint, having this level of precise data is going to be very helpful in the future. So I just wanted to go through a case that I did that sort of illustrates how you can use this technology to help with a really complicated deformity. So this is a pretty active 67-year-old guy with a actually pretty decent cuff, but a lot of deformity. And so you can see that deformity here. It's got a B3. It's actually a very high grade B2. If you look at this CT scan, there's a tiny little paleoglenoid in the front, but it's very badly retroverted and subluxated. And so the workflow for me for a case like this is I get the scan, and then you can either burn it onto a disk and upload it directly, or you can transmit it via the web. The plan comes back, and then you tweak it on your computer. So you can kind of give it the preferences that you want. And in this case, there was a pretty bad deformity, about 40 degrees of retroversion, 13 degrees of superior inclination. And so in this case, I actually chose to do a bone graft using the humeral head autograft to correct that deformity. And so in this case, we actually planned out the graft as well using the software. And you can see here on the DICOMs, the graft that we chose. So in this case, it was a 30-degree angle cut on the graft and a little bit less than 20 millimeters in maximal thickness to get the version corrected and get the implant seated in a nice position. So here we can look at where the screws are going to wind up, and that can be adjusted. Then we can also look at where the humerus is relative to the pre-op state. So in this case, it's actually 7 millimeters lateral to where it laid in the preoperative CT. But again, that was very medialized. So, you know, lateralizing this out, it doesn't over lateralize, I don't think, but it does correct that medialization. And then lastly, you can look for points of bony impingement. And so for me, this is what I like to see, which is where the tuberosity or the polyethylene is contacting the superior part of the glenoid itself. I don't like to see contact between any part of the humerus and the acromion. So that's my main goal with looking for impingement. So once you've finalized the plan, you can upload it to the software for the navigation and augmented reality. And so this is kind of the final report. It shows the graft dimensions and where we want to have the implant sit. And then using some instrumentation, we're able to replicate that graft so that it's the right thickness and the 30-degree angle cut. And you can see if you really look at that graft over on the right side, that there is a little bit of base plate that's not covered by the graft. And that's where the base plate is going to be in contact with that paleoglenoid in the front. And so this is just a little video showing kind of putting the prepared graft on the base plate. And the graft is prepared actually with the reamer for the base plate so that the radius of curvature is identical. And once that's secured, this is a longer post because we wanted to make sure we got the post into native bone. This pin was placed using the augmented reality navigation according to the plan. And then you can see the tracker up there affixed to the coracoid, and the base plate with the graft is impacted into position. You can see that it's seated flush. And then once that's in, then this is just a quick shot of how the screw targeting works. You can see it over on the screen with the biplanar DICOMs, and then just kind of go ahead once you're happy with the screw position. So this is the final construct here. And this is the x-rays of that case afterwards. And you can see there on the report, especially if you look at that glenoid implant seating circle, the blue is showing where the base plate is actually touching the native bone, which is where that little paleoglenoid was in the front. And the red is all where the graft is in contact. Then you can see we came pretty close with our inclination, within 3 degrees of what we planned. And the retroversion is within 1 degree. So pretty happy with how that turned out. One question I get a lot is how much time does this add to the case? So I've recorded the last 11 cases, and it takes about 5 minutes per case. That's well into my learning curve. But that includes putting the pins in, registering the scapula, and taking the pins out. So that's about 5 minutes, give or take. And then there's not a lot of research out yet about this. This is some early data that was presented last year at the ISTA conference. Just looking at the precision between the preoperative plan and the execution, which is within a degree and a half and about 1 millimeter. And then also looking at the post-op data from the report versus post-op CT images, which shows about 0.6 millimeters and 0.6 degrees of precision. So really pretty good for the early looks here. So in conclusion, I think computer navigation is a key technology that's going to really help us understand where we're putting implants and allow AI and other technologies to help, put the correct patient with the correct implant in the correct position. But the AR glasses are really helpful for allowing the surgeon to keep their eyes on the surgical field while still using the benefits of computer navigation. Thank you.
Great talk, John. Awesome. I think this is really helpful for us to kind of go through the understanding of how this is useful and the workflow. Pretty tremendous, ability there with that deformity case to get extremely accurate replication with regards to your plan. One of the two questions for you. One is any experience with intraoperative guides, actual physical guides, and what is your feel with regards to how this is in comparison to the use of intraoperative guides that you may have used in the past? And then the second question is, what's the plan for the humerus and what's the timetable for that? Is it already in the pipeline?
Yeah, those are both great questions. So I did go through a PSI phase, which are patient specific instrumentation. And I still use that occasionally for custom implants if I order those, which is not very common for me, but there are certain deformities where there's really no other option. My experience with those has been somewhat, they're somewhat futzy, and it may just be my lack of ability to use them correctly. But even when clearing off all the soft tissue and everything, to try to get the feet to seat exactly right, I still feel like there's some toggle on the PSI guides. And so, it's definitely more accurate than just kind of eyeballing it with a complex deformity. I feel like if you go through the effort to put a plan together, a plan like that on that deformity case takes me a long time, actually. And the overall time of planning a case plus doing the case is more than it was before, struggling through a case that's got a lot of deformity. So if I'm going to put that amount of time into it, it is nice to have something to help me execute that as precisely as possible. So the PSI guides, I think, are definitely better than not having any guidance. But I do think that the navigation for me is easier in a couple of ways. One is I tend to be a procrastinator, and I can't really get my act together to order those guides all the time enough in advance to get them by the time I do the case, because I usually will look at my cases a week or maybe 2 in advance, but rarely 6 in advance. And so that one of the nice things about using computer navigation is you could literally do your plan and upload it on a jump drive that, the day before or the day of even with the surgery. So that's nice. And then I think, having the computer guidance is certainly easier than trying to make sure the feet are seated exactly right for me. So that's my thought about the PSI. With respect to the humerus, I think, that's definitely in the pipeline, and we've been working on that. It's a little bit more challenging to figure out how to fix the tracker to the humerus in such a way that it can rotate for glenoid exposure and things like that without, moving it in some way. But we're definitely getting closer and closer with that. And I think that will, actually really help with the research end of things and understanding what we're doing for patients, because then you can have virtually exact dimensions of lateralization, offset, distalization in 3 dimensions, and you can know exactly where your humerus is relative to the glenoid. There's probably going to be some proxy calculations for deltoid tension that can be accomplished with that as well. And so all of those things I think are going to be really helpful for us to understand where we're putting the implants and the effect it's having on the patient and outcomes. So
What do you think the timetable is for that?
I think probably within the next year, but I don't know that for sure. It's we've done some labs on it, and it's certainly looking promising, but it's not ready yet.
Okay. And what was your learning curve, number of cases?
So I've done about 80 cases with this technology, and I would say, definitely the first 10 or 12 took some work. The thing for me that was the hardest was trusting the technology. Because it's interesting when you start having the ability to know exactly where the implant is in real time, you start second guessing yourself a little bit, initially at least, because, looking back at a lot of my cases prior to using this, I definitely was putting my base plates in more superior inclination than I wanted.
Yep.
Now that I can know exactly what zero looks like, it's actually a fair amount more reaming inferiorly than I was used to doing. And so at first, I wasn't really trusting. I was like, well, this is going to be too much reaming. So I would kind of, maybe abort or just adjust the plan on the fly. And then I would look at my x-ray and say, yeah, I actually tilted that superiorly. The computer was right. And so, I'm starting to kind of gain that trust in the system as I do more of these. And my inclination is looking more and more like zero every time, which I like, but it does require more reaming, which is something that's different for me. So that's one thing I've noticed as I do more of these.
Yeah. Howard and then Joaquin.
Actually, John just mentioned this thing that I was talking about, at least in my head, when we first started doing navigated shoulders. The challenge was we were doing it in anatomic shoulder arthroplasty, and I thought I had glenoid reaming and anatomic shoulder arthroplasty pretty well figured. And then I went to do my first my first reaming using navigation, and I swear it was telling me to invert the glenoid. I was like, this can't be right. And you go about it 3 or 4 times, and finally you realize that I think I was probably retroverting my glenoids a lot more than I wanted to before. I mean, I learned a lot about my natural bias and my surgical technique and the things that I was doing differently than I wanted to. So it was good for that, and it's also been really helpful from a training standpoint when you have residents to be able to let you see what they're doing without having to crowd into the small space that you have.
Joaquin?
My question is about cost. So this technology, everyone keeps asking, how much is it going to cost me? And is there a mechanism to either code for it or have a line item in the patient bill so that as we move into ambulatory surgery centers where there is a participation in benefits at the end of the year, you can see a financial value? How is that conversation in your mind?
Yeah, the cost is certainly an issue, and I think the cost was also an issue with the PSI guides. And for us, the cost difference is about the same between PSI guides and using the navigation augmented reality technology. My personal opinion is that some increased cost is justified by having the ability to execute the plan. If I'm putting in the time to make a plan, I want to make it as precise as possible. And I think that by doing that, I'm probably helping, the patient, at least I hope so. I'm helping the patient with longevity of implants and things like that. Time will tell and research will tell if being more precise and executing the plan will matter. But, right now, I think, that makes sense to me. If I'm going to put in that time, I feel like it's worth the extra cost.
Okay. And then Howard, why don't we one more, and then we'll go to Joaquin's talk.
There's to comment about costs. I think that there are 2 CPT codes, 0055T and 20985, that are available for coding for computer assisted surgery. 0055T is for using image type navigation in the operating room, and 20985 is for non-image based computer assisted surgery. And in the CC in the CC edits, it does not appear as though they are uniquely separate. So you can navigate both with imageless and image based at the same time. So both those codes could actually be used simultaneously. One of which has no value to it. So it's nice that one of them does. And I think that with regards to cost of the device itself, I think that the computer that's doing all the analysis is something that's relatively reusable. It's just the disposables that end up having some cost to it. The navigation that we use has no capital cost to have the navigation in the operating room.
So do you use those codes when you dictate your cases, Howard?
I do.
That's very useful.
Okay. It's great. Okay, thanks, John. And again, we'll circle back if anyone else has any further questions at the end. And then we'll go to Joaquin, and Joaquin's gonna, instead of augmented reality, talk to us a little bit about mixed reality. And John, if you could just unshare your screen, and then that will allow Joaquin to.
Okay, hold on a sec.
No problem. Here you go.
Thank you very much for including me in this presentation webinar format tonight, Bob. So my task is discussing how I use today mixed reality in the operating room, and there will be some overlap with the talk we just heard from Dr. Bell. And my disclosures are relevant because the system I'm going to be talking about is designed by Stryker, and I have a conflict of interest with that particular company. So I think one theme of the night is that we are very good at planning. We can plan to the millimeter and the degree, but then sometimes when we execute, we're basically eyeballing where we're going to place our pin, how much we're going to rim, and so on. When we go to the operating room and we're going to try to transfer that plan to our patient, we basically have 4 options. One would be, as we have done in the past, maybe mark with a bobby where the cross of the glenoid is and things that you understand, version inclination, depth of rimming. The second is to use instruments that come with the implant, like a checker guide, for example. The third is to use PSI, which I think is useful in many patients. And then the fourth is using navigation or robotics, which are going to be, I think, the 2 tools that are going to really transform the way we execute or plan in the operating room. Tonight, we're talking about surgical navigation, which in essence is using a computer that can track both the anatomy and instruments and understand where are they in reference to each other so that the surgeon can then place them where he or she wants. And there is multiple systems. The most commonly used is optical navigation, which is the GPS that Dr. Ruthban has used for many years. And then we have now new systems that are using either augmented reality, like we heard, or mixed reality. So going back to these different words that are constantly being used in different venues, these technologies are different. In the world of VR or virtual reality, the user is completely immersed in that digital world. So this is used mostly for training. This is one application in particular where once you get your visor on and your controls, like playing a video game, the system can train you how to do surgical execution virtually and can even rate you on how well or bad you're doing. So here, you don't have any interaction with the real world. It's all virtual. In augmented reality, like we heard before, the objects are displayed in front of you, but you cannot, as a user, manipulate that object. So wherever the objects are displayed, like in the case we heard before, the display is showing where you want to place your targets, you cannot really move that digital object in the world. Whereas in mixed reality, the user is able to combine experiences in the real world and the digital world and can manipulate those digital objects. So the reason why MR can be seen by some as an attractive solution to execute your plan is threefold. Number one, most of these elements are powered by really robust pre-op planning software. And number two, it will provide you a combination of visualizing and navigating. And today, as we heard in the last presentation, navigation requires registration, which takes just a few minutes, but can be sometimes annoying. One hope with MR is that in the future, with more cameras and more sophisticated computer power, you could potentially do markerless navigation where you don't have to register. And finally, compared to other systems that have a very large footprint in the operating room, like a robot or an optical tracker, this solution can be time, space, and cost-effective. And this is basically the equipment that you need. You need a HoloLens terminal, and then you need a little box that has the different tools that allow you to navigate in the operating room using, in this case, mixed reality. And the way this works in terms of workflow, you plan your case and request guidance, then the case is loaded into the HoloLens. You can visualize as you need, and then if you're going to navigate, you have to register, in this case, the glenoid, and then go ahead and navigate. And what happens is that the HoloLens has cameras that have different depth of view, and they can identify the location of these cubes in space. These cubes have different faces that are similar to QR codes. And then again, like in any other computer navigation system, if the HoloLens can see the cube in an instrument and the cube in anatomy, then navigation can occur faithfully. And this is a way to understand how registration happens, where the HoloLens is looking to the left at a clamp that is placed on the coracoid with this cube that has 3 faces to be seen, and then a little caliper that can be used to digitize the surface has also these 3 surfaces facing the HoloLens. And then when you get to navigate, then the guide wire is going to be navigated in a similar way. So today I'm using these 3 different ways. Early on, I just used mixed reality as simply visualization. And this is cool, but it doesn't really move the needle in my experience tremendously. But it's useful because instead of having to go back to a classic view box and look at your x-rays and CT scan in 2D, you can actually have the plan projected in front of your eyes as you are executing your surgery. You're still eyeballing, but you have the plan exactly in front of your eyes. And when you have complicated anatomy, osteophytes, difficult exposure, it can be useful to be able to project that plan in front of you. This is very useful, in my opinion, in revision surgery. One of the difficulties that we are facing as shoulder surgeons, I think, is that revision is increasing tremendously, and there are few planning softwares that can help you with revision surgery. You can plan your primaries, but not so much your revisions. And I think in revision surgery, visualizing the plan in front of you is really powerful. So this is a case of a failed anatomic TSA, where we're planning to place the base plate component in one particular location to satisfy our desire of version and inclination. And then you can actually subtract the implant that will be removed and understand where is it that your guide pin will have to be in reference to the patient's morphology once the implant has been removed. And you can do the same thing on the humeral side using revision planning. And then, like we have seen in many other computer applications for pure planning, you can then assess your range of motion, fear of impingement, and determine where you have to remove osteophytes or maybe change your implant configuration. And then if you are very picky, the night before at home, you can get your HoloLens and start to look at your plan in 3 dimensions and really understand where are you going to be aiming your implants the following day. So this is just in my office at home, the night before surgery, looking at the different implants and understanding what is the geometry that I'm going to be facing in the operating room. And this so-called clone view is very effective. You can actually move just the glenoid or the scapula in front of your eyes or the humerus. So now we're going to the operating room. We see the failed component. We're going to remove it easily in this patient. The component was placed anteriorly. As you can see, the back of the glenoid, this is still the native glenoid. The component has severe wear and is grossly loose, so it is removed easily. Then you can remove the pegs that were used for component fixation, and then there will be a defect that's going to be present. And incredibly, the defect is very well represented by the pre-op planning software that understands how to segment the implant out and show you exactly the defect you will have once the implant has been removed. Then you can activate your visualization. You can activate that clone view and bring the scapula in front of your eyes and really replicate visually where to place your guide pin, your base plate, your glenosphere, rotation, inclination, and so on, with the plan right in front of your eyes. And finally, we're going now into the application of MR to navigate. And very similar to what was shown in the previous presentation, what you want to do is register and then navigate. And most of them are the same. They will offer you a tool that will allow you to select some points. So in this case, we're using a digitizer to select the points that the computer software is asking you to identify. Typically, it's 4 to 6 points, so north, south, east, west, and then the base of the coracoid and the coracoid tip. And then after that, you're going to be painting the surface of the glenoid, and it will register thousands of points that will tell the HoloLens where is the glenoid in a space in reference to that cube that you can see connected to the coracoid base with a clamp. And then once you have your anatomy registered, then you're going to switch to a different tool that have the same mechanism of understanding the reference between the navigation cubes and the anatomy tracker, and then first choose your entry point and then change your version and inclination. And typically this is easier done in 2 steps, like Dr. Bell just mentioned in his presentation, where you first are going to identify the center of the glenoid, and the device will tell you if you are 1 or 2 or 3 millimeters away from the center. And then once you have selected the center entry point, you can then advance to the next widget that will tell you how do you have to move your hand to get into the right version and inclination. So here you can see how these little green identifiers are your references to know how far or how close you are to the center point. Once you have that entry point log, you're going to go ahead and move your hand ever so slightly to get into 0 degrees and 0 degrees, which tells you that you're going to be replicating your plan accurately. And this has been demonstrated in one study that has been sent for publication, where we operated on 14 cadaver specimens doing 7 anatomic and 7 reverses, and we assessed the accuracy and precision of this particular MR navigation tool. We have a distance between the planned and the executed entry point of less than 2 millimeters, and then a difference in version and inclination of less than 2 degrees. So I think amongst other tools, MR is emerging as a unique solution for surgical execution that will allow us to visualize the plan in front of you, which is very useful in the revision setting, and also move into the field of computer navigation. Thank you very much.
Great job, Joaquin. Again, interesting the similarities with John's presentation, and also the differences that are present. That it's nice to actually see them kind of back to back like this, to kind of highlight both in less than 10 minutes. I'm going to ask the same question with regards to the humeral side, and actually the glenoid side. So right now you're using it on the glenoid. This is in a more limited user release at this point. What's the timeline for this to become available for all surgeons to use? And then what's the trajectory with regards to the humerus?
Yeah, so this technology is FDA approved, and I think the limited user release will last probably between 4 and 6 months. So most likely by next year, any surgeon that is interested can use this tool to navigate. And then on the humeral side, I think like many other companies, Exactech and Medacta, everyone is working on the humeral side, which I think is very important, because with the stemless prosthesis and short stems, the rate of malposition is very high. So the humeral side has been neglected, and I think it's very important to really have the whole equation of the shoulder together. The timeline for that probably will be a couple of years, I estimate.
Okay. So before I'll again happy to have everyone else make comments or questions, but obviously this is a webinar not just for learning about this amazing technology of what we've just talked about, but how this is integrated with research, and how potentially to stimulate research questions, etc. And obviously a lot of this is coming online, and a lot of the work that's been done so far has been industry focused. The companies that are actually developing these products have done a lot of the work to be able to investigate these different different innovations. And what I would pose to each John and Joaquin and Howard is, how do you see that someone that isn't necessarily aligned with these companies being able to potentially use this new technology to create a new to create some research on their own, to be able to actually, what pathways do you see that other members of the ASES could potentially follow to be able to start to investigate using some of these tools once they become more publicly available? Howard, I'll start with you. What do you think? I know this is kind of a, it's a little bit of a hard question, but I'm asking it because I think part of the value of what we've just spent the past hour doing is that we've really exposed people to a lot of new technology. But then the question is, okay, how do we circle back to be able to start to investigate the technology, to be able to further identify its importance, as well as what the, there's going to be some good things and bad things that come with this technology, and to be able to maximize its utility.
Yeah, I think that, I think one of the first things would be to try to validate externally the publications that have already been done, right? So if a navigation system that's only been used by its developers has an accuracy of 1 millimeter from the preoperative plan, and someone who's not in that group of individuals is able to demonstrate that's accurate across the board, that's actually that's encouraging. And then there's the whole value proposition. And it's going to be challenging to actually prove that putting in a reverse shoulder arthroplasty within a very tight window of a plan is going to be that much better than one that is put in outside that window of the plan. But I think if we're measuring it now, then we can track it, and if we're able to track it, then we can study it, and if we're able to study it, then we can improve upon it. So I think we're really sort of in the position now where we're finally able to sort of evaluate this without the European benefits of post-op CT scans, right? Because so I think that John showed that in his pilot stuff that there's really nice correlation between his intraoperative saved measurements and the CT scan. If we're able to do that now and validate that these positions are real, then it opens up the door to a whole other area of research without postoperative CT scans.
Okay. John, any other thoughts beyond that?
Yeah, I mean, I think I totally agree. I think that, we have this power now to put implants in exactly the way we want to. We can plan it and execute it. But the problem is we don't actually know where we're supposed to be putting them, right? I mean, all the studies that, you put a specific patient in front of 10 surgeons and have them all plan it out, and there's wide variations in version, inclination, medialization, virtually every parameter that you can adjust on a plan. And so, my belief is that for a given patient, there's probably an ideal plan, but we don't know. We don't know as humans, we don't know that. And so I think, Howard's AI, coupled with this precise post-operative positioning data is going to go a long way to helping us figure out the optimal pre-op plan for a given patient, given, age, range of motion, bone quality, deformity, muscle quality, et cetera. So I think, we can all pool that data. Nobody knows, a group of industry docs is not going to have enough data just by themselves to train an AI algorithm. So, the real power of this is going to be everybody pooling their data together, is this post-operative positioning data and linking that back with post-op complications, range of motion, anterior deltoid pain, whatever you want to look at. And I think that's going to be the power of this is getting everybody on board and pooling their data together. So I think there's certainly a role for all the ASES surgeons to get involved.
Joaquin, any further thoughts with regards to how we might encourage surgeons to consider utilizing the technology to be able to further push some of the research that we're doing, and even thinking about we all kind of, Howard has a very nice structure with regards to research. John, myself, and Joaquin, we're all lucky because we're part of academic institutions, and even thinking about how to do this in the context of a private practice. But any final thoughts with regards to that?
Yeah, I think there is multiple areas that to me are very interesting. For example, in the field of AI, with the great work that Howard and his group have done, the reality is that if you read about AI, you have to validate in external data sets a given algorithm. So it would be nice if members of ASES could actually enter the data in the Predict Plus and see if it applies to every surgeon, every implant across the board. Otherwise, the algorithm doesn't have the full AI validation that is required. That's, for example, one area. The other one I think we have to think about is cost and value, because I keep thinking that going to the ceiling effect, our patients do pretty good already. And we're getting the implants within a range of version inclination that is, I think, acceptable. It's going to be really difficult to prove that by being that accurate, you dramatically change the outcome for most patients. So I think understanding how do we understand that this is of value, I think is important too. The third avenue is for the shoulder arthroplasticians that are maybe less volume users, I think that can change completely their outcomes. I think expanding this to surgeons that maybe don't have the volume that you have, or maybe less surgical volume, that can really change the needle for those patients. So I think there is a lot of opportunity to do research in this field.
You make a great point, and the reality is that a significant percentage of shoulder arthroplasties are performed by a very large group of surgeons that have very small volume, and maybe that our outcomes might not be the best, meaning mine and Joaquin and John and Howard's outcomes are not the best ones to actually track. Potentially the best outcomes to the track are people that do less than 5 shoulder replacements a year, because we might see the largest value in that value proposition in those surgeons and their overall levels of complications, readmissions, and I think it's interesting. There's always this point of where have we been over the course of the past 30 years with regards to technology and innovation, and a lot of times we are looking at things and saying, well, our ASES scores, our long-term survivorship of implants, they haven't necessarily been, the needle hasn't necessarily been pushed, or you might make that argument that they haven't been pushed by innovation. Although I'll tell you, Larry Galata has actually a nice paper that he just published on this, that maybe we actually have innovation has allowed us to be able to improve our outcomes. But how I think of that is that maybe we're looking at the wrong population of patients. And partly it's because a lot of the data that's published is from high volume academic institutions or surgeons that have extremely high volume in private practice. And probably a better group of patients to look at are lower volume patients, to see what the effect or implications of innovation and technology on those outcomes are, because it's really a very large proportion of patients that are being treated by that cohort of surgeons, as opposed to a much smaller by us. So I think this gives us an opportunity to research that. Joaquin.
Yeah, one other comment that I have, and interested in your guys' thoughts, is that I'm trying to work more on AI papers, and we have a pretty robust group now of data analysts. But to be honest, I cannot follow their methods very well. So what's going to happen to many of us as we review papers for journals is that I actually don't know if what I'm reading is high quality AI that makes sense, or someone is trying to fool me to some extent, because there is so much methods there that I cannot make a sense out of it. So maybe this question is for you, Bob, actually, as chairman of the research committee at ASES, and also thinking about, for example, JSES, or in your case, JBJS. Yeah. There may be a need to have some experts that are reviewers for AI, so that they can actually validate those papers to know if they are for real or not. We have a guy in our institution who is the president of our systems that says that AI should come with a label similar to when you buy food and you see how many carbohydrates and how many calories, so that you know where is the data coming from, what are the things that were used, and know what's the quality of the AI. Because I can tell you that I read an AI paper and I don't have the tools myself intellectually to know if it's for real or something made up. And then you throw in Chat GPT and other things. It's going to be a challenge for us scientists that are not masters in AI to weed out the good papers and the bad papers, I think. What do you think, Bob?
I think it's a tremendous question or point, and I see. I deal with this daily with regards to making decisions with regards to papers from that are submitted to JBJS, and the issue is that do I have the knowledge at the level that Peter has with regards to biomechanical studies? No, I don't. But I have resources to be able to engage people like Peter to be able to assist me in making the decisions with regards to whether or not the methods are appropriate. Same thing with, we have experts in statistical analyses to be able to help us understand the finer details of that. The problem is that within orthopedics, we don't have experts in AI. There are very, very few people. And I've tried to reach out beyond orthopedics even to be able to utilize scientists that are experts in this field to be able to help assist and review submitted manuscripts. And it is really challenging. And the reason is because they're being pulled in every direction. They're being pulled by every subspecialty to be able to actually evaluate papers in all of those subspecialties. And so, you know, I'm lucky if I can get surgeons within our field to be able to review manuscripts, never mind, scientists that are outside our field. And so I will 100% tell you it is a true problem. I think, you know, what it's going to come down to is personally, and I've thought about this, is it's going to need our society, meaning the ASES, to come to an agreement that we need to get a cohort of scientists or experts to align to say, okay, we're going to participate in the evaluation of this. And I've thought of it from a society standpoint. I've also thought of it from a journal standpoint, that JBJS, JSES, AJSM, CORE, these top journals should combine together to recruit a cohort of scientists to be able to assist all the journals, so that there's a group of people that with expert opinion that then can make a consensus opinion. That's my thoughts, but Peter, it'd be good to hear what you think about this problem.
Yeah, I actually I was thinking about it. How much AI accelerated in the last couple of years? Just the publication in the last 2 years, it was quadruple, if even more. Wouldn't it be smart or wise to implement basic parts of AI into curriculum for the future surgeons? Because it's here to stay, and it would be much more important part of our work, much more than it is now. And I think it will be much faster than we can realize. So that's one thing. And regarding the journals, I just play with ChatGPT. Shall we be concerned that people will be using it to write papers?
For sure.
How are we going to distinguish that?
I can tell you one very quick anecdote. My daughter is in law school, finishing up. And when ChatGPT exploded, I called her. It's like, have you heard of this ChatGPT? And she's like, yeah, I use it every day to write my papers. I mean, people in the universities have been doing it already for several months.
Yeah, it's out for several months, and it's already fully implemented in the everyday work of young people. So,
it's been the other issue is in the art community with regards to utilizing AI to be able to create art in you then pull in the abilities of Picasso, Monet, whoever that you would like to choose, and then you're utilizing all of that data to be able to then create art as opposed to non-AI art. And should there be some ability to be able to regulate that? And obviously artists have a strong opinion with regards to that, because it's their livelihood. And so I think it's spreading across all. It's literature, it's art, it's science. I think it is infiltrating all areas, and we need a way to be able to at least, I think, manage it in our own profession. Howard.
Just a few points. One, I think that with regards to value, I think we just published that longitudinal analysis paper looking at value over the past 15 years. And as the cost for all these implants continues to go down and the outcomes remain high, there has been a proven value to the frequent iterations of newer designs, because as the newer designs come out, whether they're augments or navigation costs or whatnot, those costs rapidly decline as further things roll out, and the outcomes for anatomic universal arthroplasty has set high. That's still it's been accepted, but it's not. It's in that pre-proof stage where you can see it on JSS if you like. With regards to the AI in these journals, one of the challenges is, I explained how I sort of went through a quick learning curve with a room full of data scientists, and I can tell you that even within the data science community, when we're looking at ways to assess large data sets, the difference between different types of algorithmic and approaches have differences in the way that uncertainty in the data set is managed. Okay, so being able to identify and choose algorithmic approaches that manage uncertainty well. So if you have 2,000 patients that have 98% of their data intact, and you have one patient missing a data point, the software does a really good job of knowing what really should be there if you have missing data points. And it's really interesting that machine learning can be effective that way. But when we look at it from traditional statistics, we would find that to be a tremendous weakness. Others might find that to be a tremendous strength. It just depends on which way you would look at it. And the final thing about having folks with us working within the journals to help us translate this, I think is going to be critical, because it's coming at us so fast right now, and those of us who are even involved in it lean so heavily on the data scientists that we work with to make sure that we're doing things right. You think about my example before about computer vision and these safety braking that happens in these cars. Okay, if you've ever been in these cars that has the cameras and suddenly it senses something and it hits the brakes automatically for you, that's a glitch in a computer vision AI program that thinks it saw something that the car needed to slam on the brakes for. Okay, and that's been released in vehicles across the US. We can't have those type of mistakes in the operating room. We can't have those types of things go on.
All great points. I want to address, there's 3 points on the before we close here from the Q&A. One is that Samer wrote in a comment, great presentations. To follow up on the comment question, how can these technologies be used to improve surgical skills training and standardized surgical skills evaluation assessment, particularly for residents and fellows? It is difficult to envision how this will materialize when these technologies are all proprietary and not agnostic. I think it's a great point, and it's another spin on actually how to use these technologies is in education. Howard kind of briefly mentioned it, but it was I think it's going to be critical to be able to actually use these from a training standpoint, and from surgeons, from that don't have a lot of experience when they're out in practice, and obviously residents and fellows. And it may be a way for us to actually, to quantify their abilities for skills prior to actually going to the operating room. It is a problem with regards to when these are not necessarily agnostic. Do you see, I guess, Joaquin and John, a potential for there to be some cross breeding, I guess, if you want to think of it, with regards to these technologies, so that there's a way that they can be used independent of the implant company?
I think for execution is unlikely, because companies are for profit and they're going to try to use the technology to drive the implant sales, in my humble opinion. But for teaching, I think so. I think there are platforms that are being built that are agnostic, and you could learn in the same visor, maybe a Zimmer Biomet or a Stryker or a Medacta or an Exact. I think for VR, we will get there. And I think Javier Duralde has a comment in the chat saying that ASES has a commitment to try to push for an agnostic platform for learning, at least.
Yeah. I'll say, so Javier comment, the technology committee in ASES is partnering with Precision OS to work on a virtual reality and teaching arthroplasty. We are ground floor of this technology, and I agree with our society needs to help guide this technology in an honest and non-biased way. We have a long way to go, but this is incredibly exciting. ASES is committed to support it. I think it's he makes a great point, and what honestly would be a very good avenue to bring up with the technology committee is the issue that we just raised, is that should there be a method for us to be able to evaluate AI technology and as a society, and have that as part of the technology committee to be able to create a cohort of scientists that we could then utilize as as researchers, as people that are associated with publications, as honestly, as surgeons, as part of the ASES, to try to understand and interpret the data that's being pushed our way. I mean, granted, our job from a journal standpoint is to be able to produce high quality publications for surgeons to be able to then change their practice. But if the surgeon can't interpret that, then it's useless. You know, it's that we need to be able to translate that in an effective way. And even if the science is perfect, that if the quality is there and the AI technology it's done perfectly, if the surgeon that's reading it can't interpret it and then translate it to their own practice, then we're really not helping anyone. And I think both of those issues probably need to be considered, at least from the ASES standpoint, is how do we make sure that the quality of AI that's being produced is appropriate? And is there a way that we can best transmit that information to people that don't have the knowledge in a way that can then effectively change patient care using that data? And so I think they're great things for us to work on, and hopefully Javier is still on, that he can. And actually, I saw Jed on as well earlier, that maybe these are things that can be thought about in the future for either now or in the next 12 months, maybe from a leadership standpoint. Last question was, could you see predictive models that were described by Dr. Routman used as a method to predict how AI can be best utilized? I think that that's an interesting question. I think that, Howard, any thoughts with regards to that? Predictive models that were described, used as a method to predict how AI can be best utilized. It's like using AI to look at AI is what the question really is actually asking, which is, it's a enigma wrapped in a question here.
Yeah, I'd have to ask ChatGPT what it thinks about that question.
That's right, exactly.
But to the previous point, I think that any type of predictive model that's not been externally validated is by definition a little bit weaker, right? So like the one thing in the Predict Plus that is not a standard collection point that most of us track is one question from the Spady index. Okay, because when of the 291 variables that we collected Spady on everybody, and no one else collects Spady. Like it's like, I was asking the folks in Europe, if any of you guys collect Spady, because I just need to get a cohort of individuals that have that one question asked, that have 2-year, 5-year follow-up, and then we can plug it into Predict Plus and see how well we did. But without that one question missing in a set of data that's already mature, it's actually pretty hard to validate it. I don't know how to answer the question about AI validating AI.
Okay, but I think that's something for the future. This has been great. I really appreciate everyone's participation. We went a little longer, but I think the conversation the discussion really, honestly, it pushed things to make me think, and to want to bring some things back to, honestly, even JBJS. And I know that Javier is taking notes, and maybe this can help our society a little bit to be able to look to the future as to how we can be able to optimize some of the newer technology that's actually coming out. Again, I want to thank Exactech for sponsoring the past webinar. We really appreciate that. And again, for the future, our next webinar is scheduled for June 27th, and we're going to start to dig into large database research in shoulder surgery. So again, thank you, and good night to everyone.
Thank you, Bob. Have a good night, everyone.
Thank you, Bob.
And thank you again.
Thanks, Bob. Good night.